Welcome to From Here to the Stars podcast, special edition panel discussion of the Arecibo Observatory, Contributions and History. We have assembled a number of experts who can speak with some authority on the subject. They are Dr. Tracy M. Becker, a planetary scientist at Southwest Research Institute in San Antonio, Texas, Dr. Gregory Matloff, an astronomer who is adjunct associate professor at New York City College of Technology, and Dr. Michael Nolan, a research professor at the University of Arizona's Lunar and Planetary Laboratory, who is also a former director of Arecibo Observatory from 2008 until 2011. I am your host, Stephen Ewan Cobb. I am not a professional astronomer. I am an amateur astronomer and have been since 1968 when I was 13. For those of our viewers unfamiliar with Arecibo, let me take about 2 minutes to summarize. The Arecibo Observatory, also known as the National Astronomy and Ionosphere Center, NAIC, is an observatory located in Arecibo, Puerto Rico, owned by the U.S. National Science Foundation, NSF. The observatory's main instrument was the Arecibo Radio Telescope, a 1,000-foot spherical reflector dish built into a natural sinkhole. Almost 500 feet above the dish, mounted on cables, was a receiver and several radar transmitters for emitting signals. This central array was able to point at different parts of the sky by moving the cables. Completed in 1963, it was the world's largest single aperture telescope for 53 years, surpassed in 2016 by the 500-meter aperture spherical telescope in China. On November 19, 2020, the telescope was decommissioned by the NSF due to safety concerns. This was because of 2 cable breaks supporting the receiver platform in the prior months. On December 1 of 2020, the main telescope collapsed before controlled demolition could be conducted. The observatory also has other facilities beyond the main telescope, including a 12-meter radio telescope intended for very long baseline interferometry with the main telescope, and a LiDAR facility whose research has continued since the main telescope's collapse. Also, I'd like to mention that I did a Google Scholar search, which searches peer-reviewed journals, and found a paper authored by 4 people, 2 of them on today's panel, Dr. Becker and Dr. Nolan. The paper described how they used the big dish at Arecibo to bounce radar waves, or radio waves, off a nearby asteroid, a near-Earth asteroid, indeed the first triple asteroid in 2008. Having talked now for far too long by my own measure, I would like each of our guests to go down the line and introduce themselves, tell a bit about their research interests, and about their connections with the Arecibo Observatory, or also how the data from the facility contributed to their work, beginning with Dr. Becker.
Hi, yes, thank you for having me on. And the paper you're referring to is actually my first ever scientific publication. Because I got my start in planetary science research at the Arecibo Observatory in 2008. I worked with my 2 advisors, Dr. Ellen Howell and Dr. Michael Nolan, who's here with us today. That was actually my first research experience that I had, was working at the telescope in 2008. I was so excited to be going to one of the most famous telescopes in the world. I couldn't believe that I was accepted to do that summer internship. And things went really well, and I ended up coming back in 2009 and then again in 2012 to finish up the project. So I can really credit Arecibo with my start in planetary science. Okay. I'm currently at the Southwest Research Institute, and I do research on a number of things, including working on the Europa Clipper mission, but I also spend a good amount of time still working with the observatory. I'm currently the lead for the science communications for the observatory, working with the University of Central Florida, which currently manages the facility.
Okay, Dr. Nolan.
Hi, I'm Mike Nolan. I have spent most of my scientific career at the Arecibo Observatory. I'm currently the science team chief for the OSIRIS-REx asteroid rendezvous mission, which just went to the asteroid Bennu. And that comes from my work at Arecibo, that in 1999, I observed that asteroid with Arecibo, specifically with the idea of planning and studying these asteroids for their potential visitation by spacecraft in order to plan spacecraft missions. And then, of course, we did just that, and that's how I got where I am today. So I was at Arecibo for 20 years, started there as a postdoc. Along the way, I was the observatory director and the head of the Planetary Radar program. Most of my work involves studying asteroids, and in particular, asteroids as they relate to meteorites, and the formation of the Earth, and all of the things that got us here. So yeah, and people have been talking about how interesting it is to be there. I said I would often take people up to see various parts of the telescope, and it's one of those things that people said, "Do you ever get tired of this?" I said, "No, I never get tired of this." I'm always happy to take people up here because it's really just one of the coolest things that people have ever built.
Mm-hmm. And Dr. Matloff? Dr. Matloff?
Well, first of all, Stephen, thank you very much for having me on this. Basically, my research most of it has involved applications of interplanetary and interstellar photon sailing. And I've done a lot of it in collaboration with Les Johnson and his team at NASA Marshall. I've also done a lot of teaching at City Tech. I took advantage of early retirement from my tenured position in 2011. I've been very, very happy to be an adjunct since then, because if any of you have tenure, you know it's not really a lot of fun. It's very secure, but it is a lot of committees, a lot of, well, I want to say politely, garbage, should we say, but you have to do it. My relation with Arecibo professionally is that, first of all, it really turned me on in 1974 when I heard about the famous message to M13. And I realized that this device that we have constructed could basically communicate with itself over galactic distances. And that's an amazing thing. And it changed my life because in 1982, when I was an adjunct and a consultant, I met my wife, C. Bangs, on a blind date. And I had no idea what was going on. We started talking. I learned that her father was a retired professor in the hotel school at Cornell. And he had gone to Puerto Rico as a consultant to the University of Puerto Rico. And what had happened then is they visited Arecibo, and she was turned on as an artist by this. And that hooked me. This was the beginning of what was going to really change my life. But I hadn't been there forever. Finally, a few years ago, since as an adjunct professor, I had more time, we took a little trip to Puerto Rico. We rented a car one day and got away from the beaches. And we drove along the main road, and I forget the number or name of that road. I'm sure that Mike and Tracy know it well. And she was driving, I was navigating. She'd been there before, and she was ready to laugh. And I know now why she was laughing, because we get off the road at the appropriate exit. We follow the little signs. And I'm noticing we're getting into the rainforest. We're getting into the jungle. And there are occasional farms. There are chickens that you have to stop for as they cross the road. There's an occasional cow, unsupervised cows. And I look at C and said, hey, we're lost. We're never going to get out of this. Where is this place? And she laughed and she said, nope, keep driving. You're doing a good job. No, keep navigating. You're on the right track. And suddenly we see this pylon, which just jumps out of you as you go around a turn. You go into the visitors parking lot. You walk maybe 500 meters, and there you are at the observation deck. And, I've seen pictures of this in 1,000 publications. No picture does it justice. And I really wanted to get into it. It was a Saturday. There was a young woman who was the docent of the day, an undergraduate or master's candidate at University of Puerto Rico. And she asked if anybody had any questions that she could answer. Maybe she couldn't. So since I have a close friend, Claudio Marcone, who had given a talk there, and I know a lot about Claudio's work on SETI, I came up with a rather nasty question. I said, gee, I know that you're doing a lot of work on asteroid mapping. on basically taking in information from other stars and maybe looking for SETI signals. Oh, maybe you can tell me when you do this, do you use Fourier transforms or KLT? And she had stopped her in her tracks. And she said, I have to ask you, a scientist, about this. And I really thought this was going to get me into the control room, but it was Saturday and there were no scientists there. So I never got into the control room, but it was an amazing experience anyway.
Mm-hmm.
And when the thing began to collapse, in the first stage of the collapse, I was asked by, why can't I think, well, one person, Paul Gilster,
From SETI
really
Dreams?
contribute to his piece in it. Yes, SETI Dreams. And then for Denton Abel at the Hayden Planetarium Museum of Natural History to get involved in some of the discussions which have led into the possibility of maybe a recovery effort. So, you know, but I can't say I've ever observed there. I have not. I'd love to.
Okay. Because most of our viewers are not just just casually interested in astronomy, they're mostly enthusiasts of astronomy and space exploration. One of my questions is, everybody knows that this is a famous telescope, and it was venerable, it was admired, mostly because it was so large, but its largeness gave it special abilities that other telescopes did not have. And so, and I know you could all answer this question, but I'll almost let you fight for it. What was the extra power that this telescope had? And I'm guessing it was the ability to gather radio signals, but I don't know the technical aspects of that. And so if you could, one of you at least, could address that. What abilities did it have before other telescopes ever had them? Maybe I'll throw it to Dr. Nolan since he was the director.
All right. Well, I mean, it was explicitly built to be the largest instrument of its kind by a lot in the world. There were other big radio telescopes. So it was originally actually designed to study the atmosphere, with the study of planets being a secondary purpose. So the design was modified to study planets, because of course to study the atmosphere you only have to look straight up. But they made it so that it could point, so they could study the planets. And they were looking for a particular property of the electrodynamics of the atmosphere, and figured out how big the telescope would have to be to do that, and said this would be something like 10 times bigger than the next largest telescope at the time, and would be really, there were some beginning studies of the planets, and said, you know, this would be a whole lot better for those too. So it was really the radar work that started it off, and the study of the solar system and the atmosphere. People say that there was actually a calculation mistake and they didn't need such a big telescope, but that's not actually true. What it is they didn't understand the physics, which they knew. That was the whole point, is they didn't understand the physics. And the thing they were looking for was modified in some other way. And it turns out actually that the actual literal effect that they were looking for was discovered in something like 2010. There's a very faint signal on top of the much brighter one that was discovered right after, right as it was being built.
Okay.
So yes, it is the biggest. And for doing the planetary radar work that we do, if you go and do the arithmetic, it turns out that it's something you can just barely do. So studying the planets and asteroids with radar, it's right on the edge of possibility. And actually, when I do the arithmetic, it's almost, gee, we actually got lucky that this was true, that 1,000-foot dish and 1,000,000 watts will do the trick by a factor of something like 100 or 10 or something. Not a billion and not one, but it's, so you need a telescope about this big to do that work on any sort of consistent time scale. And that's was really its biggest strength for the work that I do, which is specifically the asteroid work.
Okay. My first awareness, I guess, was around 72, 74, when concerning radar, bouncing radar off of an alien body. It was the moon, and it was Apollo 17, the orbital module, used two different frequencies, and I don't remember the numbers right now, but to bounce these radar signals off the moon and record the bouncing back in order to look through the regolith to the rocks below and map them. And I was just fascinated by that. And this sounds very much like that, but not just the moon, but also asteroids. And I'm wondering, is there penetration into these asteroids, and is that part of the study?
It is. We're just now starting to look at that. So on the moon, you have the advantage that you have basically a round ball with topography and rocks. When you're studying asteroids, you can see a picture of one behind me. That is actually a picture from asteroid Bennu. The distinction between the shape and the topography and the rocks is very difficult to make. So yes, this radio signals are almost certainly propagating the ones we use about a meter or two into the surface. And we're now starting to look at the reflectance properties in more detail at the actual reflectance to see if we can do some of that. Historically, until we sort of got a picture of what we were looking for, all we did was say, okay, I want the rough shape. But just now, I have a colleague who's at Arecibo as a postdoctoral student who is working on how it is we need to process the data further to be looking down. And we are talking about, okay, if we build another Arecibo, if we build another big facility, we do want to have this sort of a multi-frequency capability so we can look both at the shape and down into the surface.
Most people are aware that the main dish was not directable. It was aiming the telescope was done by moving the focal point, the focal apparatus around, which was slung on cables. That sounds, because the central piece, the focal piece, it weighed, I believe it was it 500 tons or something? It was some massive amount. What was the weight of it? Do you remember?
It's 900 tons.
900 tons. That sounds like a lot of material to be moving around on the ends of cables. Can you describe something about the engineering of the motors? How powerful the motors had to be for that?
Sure. So if you look at the picture behind Dr. Becker, which is where we have a picture of the telescope.
Okay.
Most of that 900 tons is that big sort of lit up structure, which does not move.
Oh,
right?
okay.
There isn't a 900 ton moving structure. You can also look on my shirt here, right? There's the dome and the line feed antenna.
Okay.
So there's a big triangular structure that's static. Sort of this arc-shaped structure down below turns around in a circle. So that gives you the direction you're pointing. And how much does that weigh? I think that weighs about 200 tons. And then the dome itself, so the antenna is not, the long line feed antenna isn't that heavy. It's probably 35,000 pounds. The dome was about 200,000 pounds. And so when this big arc structure is moving, it's just turning around on a circle that has been very carefully leveled. And so it doesn't take a lot of work to do that. There were 8 motors, yay big, that turned it. It doesn't turn very fast, right? I mean, all it has to do is track this guy. It goes a little faster than that because it has to track asteroids. It would take 15 minutes to turn one complete circle. The dome actually had, I think, 32 motors because it had to pull this, you can see it's an arc, and so it has to push against the force of gravity to pull that dome up and down along the arc. And so those were fairly big motors. But there's standard commercial technology. It was not, it's a big thing, but it was certainly not the biggest thing. And that would it took about 10 minutes to go all the way from the bottom to all the way to the top. So basically you use gears, you go slow. It doesn't take a very big motor as long as you're willing to wait a little while. And since the stars and the planets don't move very fast, it all worked out pretty well.
Okay. Greg, Dr. Matloff?
Yeah, thanks. Greg can do, but that's okay. Thanks. I have a question for Mike, maybe for Tracy about this. The initial version of Arecibo was constructed using 1960 technology. And it's, of course, these are big hanging pieces of hardware, some of them moving, some stationary. in 2021, assuming that we're able to rebuild something, which seems like at least a good possibility, can we reduce the weight of these things somewhat and get the same kind of performance?
If you want to build Arecibo back more or less the way it was, I think cable technology is significantly better. And that's huge because, right, everything you can lighten on the way down improves the payload. To be honest, I think that the main structure, it was steel. Steel is steel, and it hasn't changed dramatically. We've been using it for millennia. We understand, and so I think they can do some numerical modeling of the details that wasn't possible in 1960, but actually they did have sort of they did understand the physics, and so they did know the how relatively strong each piece had to be. And if you look at it from a distance, it looks like it's basically one triangular piece, but each of those beams was specifically sized for precisely the job it had to do. Again, they couldn't do some of the dynamical modeling that we can do now, but the basic structure of that, I don't think would be very different. So I think it would look perhaps a lot like it does now. We've been talking about you might want to have it a little lower and a little more curved. That would probably save some weight. And again, the cable technology, I think, has improved noticeably, and so they would be able probably to, well, given our experience, you would probably use the same amount of cable and just have it be more capable. But so it would, in principle, you could build the whole thing out of carbon fiber, but it's really big. Again, there is no way you can sort of see how big it is without going, right? This catwalk is a third of a mile long.
That's really the source of a lot of the fame of the instrument is its size. It was so massive. It's astounding to me that they built what was it, a 500 meter, or I forget what, I just read it a few minutes ago, in China, that much larger than that facility. But I have not studied that facility, so I don't know how it's operated or how it's aimed. One of the things that surprised me about Arecibo was that even though it's a fixed mirror and moving only the aiming part, the receiving part, that it had an aimability, so to speak, of 38 degrees, I believe, 38 degrees north, and I think 1 or 2 degrees south. Of course, the Earth rotates, and so you were able to point it to different parts of the sky just from that. But still, almost a 40-degree range of aimability, so to speak, was pretty impressive. Mm-hmm. Let me see if I can get Dr. Becker talking again.
Yeah.
Have you anything to say without a question, simply on what's been said already?
Sure. Yeah, I would just add that the question of what could we do next with Arecibo is one that the community has really come together around. It's been impressive. Hundreds of scientists gathering from the moment the second cable broke, twice a week, talking about what can we do next, like what can we do to potentially prevent what did end up happening with the collapse, or what can we do, what do we do next? And so the scientists, engineers at the Arecibo Observatory have been working really hard on this question, and the entire scientific community, hundreds of people who are just equally as inspired as everyone talking here, including yourself, talking about how inspired they've been by this telescope, are working on the solution for the next version of the telescope. It's possible that we rebuild in a similar way that it is now, with some of the improvements and lessons learned. And as Dr. Matloff was saying, we have better technology now than we did in the 60s. So, maybe doing things to try to lighten loads or different kinds of powering capabilities. But there's also interest in kind of a whole new design as well, still keeping it in Puerto Rico, but potentially, looking into other advancements in technology today to see if those would maybe be a better solution or not. That's all still to be determined. In the last month, people have poured hours and time into trying to figure this out. So there's a lot of interest. There's a lot of support in the science community, and we're working hard on figuring out what's next.
Well, let me ask you specifically, and maybe you don't feel, that you've researched enough for the answer, but still, I want to ask you, with the central piece falling down, Of course, much of the dish still exists. It was damaged, but still exists. How much good is still there that could be made use of? How much of the facility is still useful and would not be necessary to rebuild? And how much, I don't know, you wouldn't be able to put a number to it of how much money it would need, but still, how much good is there still there that could be made use of?
Yeah, I can start, and I'm sure Dr. Nolan could add. But you know, the towers, part of them, as designed, did come down when the dome fell. But you know, some of those supports are still there. A lot of that tower structure is still there. Parts of the dish are certainly still intact, although that wasn't necessarily the most expensive part that we would need to replace anyway. So, and of course, all the buildings and the extra facilities that you were referring to. There's also even a remote optical facility. There's a facility being built right now called Carla, which studies more of the ionosphere and trying to look at the Saharan air layer, so the dust that comes over from the Sahara. Those things all exist currently, and they're where they are because we want them there. So there's still other facilities that are that would work with the telescope being built in the same spot that it's in. So there's some things, you know, of course, all the buildings, all the computer systems, everything else that's still there. So yeah, I couldn't put a number on it, but there is interest, and there is potentially some savings by just kind of utilizing what remains in the area versus just building in a whole new site.
Dr. Nolan, when people look at the photos of the place, with the cable and the central piece down, it looks pretty awful. It looks like mostly the whole place is destroyed, but most photographs don't include the building, the offices and such. How much? I mean, you probably can't put any kind of price to it, but maybe a percentage of the total cost of the facility. How much has been lost? Was it like 20%, 50%?
Oh, it's more than 50%. The telescope, everything went to the telescope. So when I was in director, we were having funding problems, and people asked me, "Why don't you fix this? Why don't you fix that?" I said, because we're here for the telescope. If the telescope isn't here, there's no reason for us to be here. So that's where all of the resource really go. So something like 80% probably goes to that. You're right. I should be careful. Because people always forget how much the nuts and bolts and wires cost. And there is a lot of that other infrastructure that is there and is fine, that we do have to remember you need and is already there. Like there's a lot of wire that's been laid, there's a lot of cable, there's power, a lot of that stuff so I should really be careful that in my head, it's most of it, but 50% would not be surprising if that all the other stuff really does add up to that. As Dr. Becker said, we can probably, I don't think we wouldn't like reuse it the way it is, but for example, if we put up a new secondary, all that aluminum still on the ground, it's not quite so telescope shaped anymore, but you could still do some, like especially some initial atmospheric work that's much less picky about where you point and just needs a big piece of aluminum. And so what it would do is let us kind of get started with some stuff while we're building that. And that was actually done so there was a big upgrade in the 1970s. And the old mesh we always called it chicken wire. It was actually more like a hardware cloth. And they replaced it with the aluminum panels that you've probably seen pictures of, and they just did that a little bit of it at a time, and it slowly got better. And so I think that's the sort of thing that you could say, okay, the aluminum's there, we can still do some things while we're fixing the rest, and that would be of value because it keeps it moving, right? You get to see sort of initial work sooner.
Okay, Dr. Matloff.
Yes, I have a question from either Dr. Nolan or Dr. Becker.
Okay.
In 2007, I did some work with NASA Marshall people on what's going to be a very close approach to the Earth in 2029 by asteroid Apophis. And if it happens to hit a mathematical device called a keyhole, it'll be back 7 years later and it'll smash into the Earth. It's about 200 meters across. And I know it's very important with something like this to have extremely good radar, extremely good mapping on the system, on the asteroid. Do you think if we do a repair of this, it will be ready in time for the 2029 close approach of Apophis?
So I'll start by saying that this is a really good point that people don't always think about with radar. In addition to being able to kind of image and determine the shape and structure of a lot of these asteroids, the biggest, I think, in my opinion, importance of the radar is that you get extremely precise velocity, position, direction of these asteroids, and we can track out for a century sometimes where this asteroid's going to be. And you can do this with other measurements through standard images and things like that, but you can do it so much better and in an instant with the radar data, which is what makes it so powerful. Apophis was, of course, one of the targets that we wanted to observe with the Arecibo. And I would hope, I think whether or not it'd be ready in 2029 for that event is really dependent on funding situation from whoever is able to fund the facility rebuild. I mean, it's going to be time to design and time to construct, but a lot of that is mostly dictated by funding rather than timing to build, I think. That's my thought.
Okay.
Thank you.
So the original telescope was proposed in 1958 and commissioned in 1963. If the will's there, it can be done. There are a lot more rules now, a lot of them for good reasons. As an example, they did a lot of the initial work in the site, but with blasting, explosive blasting, which is now forbidden in the area because there's an extensive cave system and it would disrupt some pretty important things that just people didn't pay attention to then. So, but nonetheless, if the will is there, there's no reason it couldn't be built in that time. As Dr. Becker said, it really depends on the funding. I've been in several of these sort of projects. Once, years ago, we were talking about, are we ever going to go to Mars? What would it take to get us to Mars? Oh, we need these years of planning. Somebody said, that's just because we don't have any money. If you tell us you want to go to Mars and hand us the money, I'll have you plan in 2 weeks. And it's the same kind of thing. If somebody says we commit to this, right now, as Dr. Becker pointed out, the science is talking about ideas about ways we might do this. And we're still at that sort of speculating on cool new things before we sort of narrow it back down. If somebody said, give me a plan in a month, and here's the money, no problem.
Okay. Earlier, when I was asking about what still is good there, I was thinking even if you had no building, no electricity, no structure, and just the sinkhole, that alone is something that of value. So that if you have the building, with the offices and, places for people to work, then that's something. And then, of course, the people already run electricity to the facility. It's got a lot of infrastructure, I think. Although, again, as you mentioned, most of the instruments were located on the piece that fell, and that was some expensive stuff. Let me ask this. We mentioned a number of asteroids that have been targeted with the radar from this facility. How many asteroids have been researched? And I mean, not just, that we got some images of it to find out what shape it is, but also maybe its orbital parameters, because that's important to near-Earth asteroids, the potential danger of them. And you may not have these, numbers right off the top of your head, but I'm curious, do you know roughly how many asteroids have been researched and measured with them?
Yeah, so the Arecibo Observatory in 2019 broke its own world record of detecting asteroids. And I think the number came out to be something like 123 asteroids detected in 2019. And previous years, it was something maybe more like 60 to 80, starting around 2012. So
when you say detected, do you mean newly detected, new discoveries?
So the observatory doesn't typically doesn't find the asteroids for the first time, because we have it's a very specific pointing of the radar. So we rely on the detection from the discovery from images and more traditional ways of looking for asteroids. And then the observatory would then point its very narrow beam of radar to that asteroid. And so so great question. When I say detected, I mean actually got a signal back from the asteroid from our radar data. And as soon as we have that, you do have all of that information about its position and velocity. And then it really depends on how far away and how big they are, if you can really get like a shape and a structure and other some of the other parameters. I don't know if Dr. Nolan wants to add to that.
Yeah, so it's really it's the astrometry that we get first. If you look at one of those radar images, the pixels are anywhere from 15 to 100 meters, but those are absolutely located in space. And so our hard work that we spend a lot of time on is in processing images to get details about the asteroid. We send the astrometry usually within 20 minutes.
Wow.
Impressive. I'm curious, most of my interest in astronomy is observational. But when a new object, say a new asteroid, has just been discovered, there's no data on it, and they've got photos of it, and they're able to isolate its location in right ascension and declination, but not distance. So was Arecibo and other facilities like it, were they able to narrow down its distance, which would allow them to produce the orbital parameters for that object? That sounds like the main strength.
Yeah, that's exactly what we did. Is that the radar measures distance and it measures speed, and so we would get that measurement of the distance and speed usually within about 10 or 15 minutes of starting our observation. What we called course ranging was a measurement of to a 600 meter accuracy, not precision, accuracy, and so we immediately got. Here's the range. So if you know where it is on the sky, I'll tell you how far away it is and how fast it's moving in that direction. And it can dramatically improve our understanding of where it is.
And could so this also do comets as well?
We can do comets too. Comets tended not to come as close. And so, but we did do the same thing with a few comets. Schwarzmann-Mach 3 broke into pieces, and we actually got distances and images of several different pieces. And so that's actually one of the things that was kind of fun and kind of less fun sometimes. Is somebody would discover an asteroid, say its orbit is extremely uncertain, but it has a chance of hitting the Earth. And I remember one time there was there's this asteroid, it has a 5-digit designation, and at 3 in the morning on Sunday we can observe it at Arecibo, and that'll improve the orbit. 3 in the morning, I don't want to go at 3 in the morning, so wait. I really don't want to be in this issue. Well, I could have saved the world, but I didn't want to get up. Okay, we'll go do it. And it turned out to be a very cool observation. It's one of the, it's deciding you want to get up at 3 in the morning is hard. The actual getting up isn't so bad. And it's kind of funny with the radar, particularly at Arecibo. Arecibo can only point to any one object for a couple of hours. And so my previous experience doing astronomy is you go there at sunset and you stay there all night, right? At Arecibo, it's a couple of hours. So if the observation was at 3 in the morning, you get up at 1:30 and you go in. And in some ways that's easier, but in other ways it's harder because you actually say, well, I should get some sleep before my observation.
Okay. I could nerd out on all this stuff, but I want to ask for personal stories, maybe some weird anecdote or some faux pas or some goofy thing that you didn't have to do it yourself, but maybe you saw somebody else do it. Just in order to wind up the show, and that is if each of you could take a moment and Greg, you've already talked about C. Bangs, your wife, and how she led you there basically by surprise. But Dr. Becker, if you can, lead us off in this. And if you need to take a moment to think, that's fine. Again, it's an edited show.
Yeah, this is a good question.
If you'd like, we can come back to you.
Okay, yeah, come back to me so I can think of a good story.
Anybody have one ready? They're ready at the.
So the one I told is one of those, really. So that probably works.
Okay.
A couple of other things is I really was there for 20 years, and so there aren't that many funny personal stories because I was so much a part of it, and it was so much a part of me all those years. And so, I mean, there are a few, right? People will ask, again, you can see the catwalk in the background. It's like, they said, oh, did you ever walk there? I said, I've never walked up the catwalk. I've run up it a bunch of times, because the reason we have to do it is we have a very short time. And the only reason I go up the catwalk, there's a cable car that's faster. And so the only reason I would go up the catwalk is if something's broken and I can't use the cable car. So, and as you can see, I'm kind of large. And so it was like, yes, I can run up that catwalk if need be.
Okay.
And go up and down the 7 flights of stairs at the top. But the other one really was, the personal thing really was, I went there in 1995, and in 1999 we started really observing asteroids. I knew when I applied for the job, I said, I want to go study these asteroids as preparation for space missions. And then as my space mission was taking its data at Asteroid Bennu, it was like, yes, I went there in order to do this, and here we are today, taking these data of the Asteroid Bennu, which was chosen in large part because we had those observations back in 1999 and 2005, so we knew where it was. We could use that information to plan the mission. And so you say, so the entire cost of Arecibo over its entire existence is something like is a few $100 million US, 2020 dollars, 2021 dollars, I guess now I have to say. But in that time, yes, we planned this space mission. We won a Nobel Prize. We discovered the rotation rate of Mercury. We did all these other things. So we said we spent this money. We did all these things, and then we made this one measurement that was critical in planning $1 billion space mission. And so that's it is difficult to tell funny personal stories about things that are so important to me.
Okay. Yeah, justifiable. Anybody else?
Sure. Yeah. And actually, I did want to just add one thing to some of the stuff we've been talking about before I get into my one of my funny stories, I suppose. We talked a lot about the radar, but the Arecibo Observatory obviously did a lot more. We talked a little bit about the ionospheric studies, but the astronomy, it was really big. The Nobel Prize came from the astronomy measurements of binary pulsars. And, study of pulsars really, is part of this huge program right now called nanograv, trying to look for gravitational waves, really still pushing the limits of our understanding of the universe. Arecibo was still very much on the front line doing those kinds of science until the day it stopped operating. So I think that's really important. And the other thing too, I mentioned the scientific community being so supportive of a rebuild of the telescope, but so is the Puerto Rican community. And I think that's really important to remember that the island of Puerto Rico really does treasure the telescope as well. So it's important to more than just science, but to the people there. And for my funny story, I guess I'll go with when I said, my first internship in space was at the Arecibo Observatory, 2008. So I had been in college, and we got to stay in the cabins that are on site. And if you've ever seen the movie Contact, the Matthew McConaughey is in one of those cabins with oh no, now I can't think of actresses' names.
Was it Helen Hunt?
No, with
Jodie Foster.
Jodie Foster, thank
Jodie
you.
Foster.
Sorry.
Yes.
Oh man, I knew that was gonna happen. Yeah, so Jodie Foster and Matthew McConaughey are in one of the cabins. And of course, so when we get there, all the interns, there's a couple cabins up there, but there are two big ones. All the young men that are at the observatory for their internship are in one, and all the young women are in the other one. And so of course we're trying to sit there, figure out which one is like that romantic scene with Matthew McConaughey. And so, we were so excited about it. And of course it was the boys' cabin. So it turned out it wasn't our cabin. But yeah, those were the kinds of things, like a lot of people said they were inspired by these movies and by the science that was being done by this telescope. And I'll just add that, like, one of the coolest parts about getting to work there was that, you look out your window or you go outside for some air, and it's just there, and it's so massive. And as Dr. Matloff said, it, like, no image does it justice. It's breathtaking every time. And at night too, it's lit up and it's beautiful, and the coqui frogs are chirping all around you, and it's just the skies are so clear there. It's a really incredible feeling while you're there. And so yeah, I'm really hopeful for the next version of it.
Okay. Greg, you got anything?
I'd like to add a little bit to what Dr. Becker just said. A few years ago at a meeting, I had a nice talk with Jill Tarter. And of course, Jill Tarter is the model for Ellie Arroway in Contact, who was played by Jodie Foster. And Jill, when she gives a talk, she'll stand up and say, "Just call me Jodie," because Jodie did a very good job. And what Jill told me is that there was at least one thing in the movie that was completely inaccurate, and that was showing the actress in the visitor's parking lot, sitting down with earphones on her head. And she, of course, is trying to pick out SETI signals. And what she said is, that's nonsense. You don't do it like that. You program in what your observing strategy is going to be. And you also tell the program to wake you up if there is a message or a possible message, and then you come running. You don't sit there with earphones on waiting.
So it was a nice scene for the movie.
It was a scene, but it was totally inaccurate.
Okay. Dr. Nolan?
Yeah, I do have one other. It's not really a personal story, but it's a story about how people work at Arecibo, and the SETI activity is a good part of it. Is because it was a remote facility with the history it had, it was a very hands-on facility. People would come and with ideas, oh, I want to do this thing, and most things it's all computers. Even at Arecibo, when we left, there was still these patch panel cables, because that way, and I always said, well, I would like a computer controlled thing for its better performance sometimes, but I still want the patch panel, because if somebody says, can I do X? I look at the patch panel, think a minute and say, yep, we can do that, and wire it in. And I have a couple examples of that. One is some people with the Lunar Reconnaissance Orbiter spacecraft wanted to do a test, and they brought 2 racks of equipment that were supposed to feed a signal into the radar. And on the day, it didn't work. So I said, well, what does it do? What are you doing with that? So, oh, we have this code, we have this synthesizer. All right, what frequency, what kind of code? Yeah, I got one of those. So I patched it. So instead of their 2 racks of equipment they couldn't control, I said, okay, I'll run mine. Just tell me which one to do. Okay, here we go. We're off. We were 5 minutes late. The other one is the SETI work at Arecibo. There was a kind of big story how it kind of got defunded, but the people who did the SETI would still come with a lot of really good ideas. And so for one thing, they were really good at finding artificial signals. And a big problem at a radio telescope is interference from terrestrial stuff. So they were very good at helping us find and eliminate the interference we were causing ourselves, because they said, okay, there's this signal, that's the artificial signal that has the following properties. Said, oh, well, that sounds like the air conditioner. Let's go shield the air conditioner. And then one day they said, if we brought us something, so we had this radio astronomy pixels are big, and so they said they were bringing us. We had a brand new 7-pixel receiver. That was the biggest new one we had, and so they said if we brought something to go sample that, we won't tell you. We're not going to say what to do, but we just want to piggyback on whatever observations are made. Can we do that? And we said, you bring the equipment, we'll plug it in. So there was a very big effort to do a lot of that, the cooperative things, and a lot of the reasons, like for example, one of the reasons they were so big on pulsars, which are these varying signals, is that the radar people knew how to take data in a way that let you do those kinds of observations. Most astronomers are looking at galaxies. Galaxies don't move real fast, so you take long sets of data and average it all up. If you want to look at something like a pulsar, it's something that goes real fast. And so the interaction between the communities really helped us do all of those different kinds of things that we did. The radar, so then later when the pulsar community was actually better funded and the radar was having some hard times, I looked at one of their machines and said, does this do this and this and this? Could we use that? because they then were the up and coming people, and that was one of the low points in the radar set. So the cooperate, and that's not something that happens at very many telescopes, because at most telescopes, the staff does it. There's a lot of design and those things, and you're not left with something that a user can really interact with. Part of that is because Arecibo was so big that it had to essentially be unconditionally safe. That because there were a lot of telescopes is like, okay, don't hit this into that. It's like the thing is 1,000 meters away and it's enormous and it's got so many horsepower behind it. There is no way to say, oh, please don't break that. It has to be, no, you can do things, but we've arranged it that there really isn't a way for you to break this.
Okay.
That it might not work, but you're not going to hurt anything. And so we were able to do all kinds of stuff. One sort of standard thing is an astronomer would show up and say, I want to do X. And one of the staff people would say, really? You want to do that? And there were two options. One is they'd say, I think you want to do this, it'll be a lot better. Or we had a staff member who was famous for arguing with them. You don't want to do that because of this. You don't want to do that because of that, and this and that, and this and that. And they would often leave thinking it was ruined. And then the next day they'd show up and that same person said, okay, I wrote these scripts. I tested them last night. Here's some test data on this galaxy. I think it's ready to go. See what you think. So he was just arguing with them to find out what really were the goals so that he could implement them for their next observing session the following day.
Awesome. I gotta think. Oh, go ahead.
I'll just add to what Dr. Nolan's saying is, when you get to the observatory and you go into the actual commanding, building where all the computers are, where Dr. Nolan was talking about these open face systems, it is amazing because you know that this is one of the premier facilities in the world, and everything is from like 1965. It looks like the compute. There's tape decks in a whole room. There's computers where you're to operate the radar. You literally have to take a wire and unplug it and put it in a different position and put another wire in another position. And there's like several of these that are all crisscrossed, and the people that have been operating this for forever, they know exactly what they're doing and which one goes where and makes it all work. But there's an oscilloscope that you see, like, you have to make that work, and it's so funny because you imagine, and like when I got there in 2008, that you would have these fancy computer systems that would just make everything go. But as Dr. Nolan said, one of the surprisingly powerful parts of the observatory was that you could actually still tinker with things and change things pretty fast, because you kind of had everything at your hands the way that it was designed decades earlier. So it was definitely funny. It's one of those moments where, when you watch things like The Martian and the Jet Propulsion Lab is this beautiful, crazy looking modern high tech place, and then you get to Arecibo and as Dr. Nolan said earlier, the money was always about focusing on the science, and so that was part of it. But also it was a benefit too, and it was just very funny to be in there and see kind of what everything looked like, and see computers that were probably built from well before I was born when I got there.
Right. I mean, to say that there was the most modern things as well, but of course they were behind the scenes and you didn't see them.
Yeah.
People said, "Oh, your receivers are old." Said, "No, our receiver." It turns out that TRW had one best wafer that had the magic transistors on it, right? So TRW was my old fabrication company in Los Angeles, and they built the transistors that were the first amplifier, right? The thing that really sets the telescope. Mm-hmm. And they said there was this one magic wafer. Those transistors were the best. We had 10 of them, and so we had the most sensitive amplifier that you could possibly build. But of course, it's up in the telescope in a doer, and nobody can see that. What they see is the big old gears. It's like, yes, but that's because we put the $250,000 in that receiver, so that it is the most exquisite receiver you can possibly build, and we didn't paint the box.
Awesome. I thank you for all of you for coming and participating. This was great stuff. And that's about it. If all minds are clear, we are done. Thank you again.
Bye-bye.
Thank you so much.
Bye-bye. This has been the From Here to the Stars podcast, special edition panel discussion of the Arecibo Observatory, Contributions and History. We'd like to thank our distinguished guests, Dr. Tracy M. Becker, Dr. Gregory L. Matloff, and Dr. Michael Nolan. This is a production of the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. Find us online at irg.space. I have been your host, Stephen Ewan Cobb. On behalf of all of us here at the Interstellar Research Group, I thank you.